All right, let's just dive right into this explainer and totally demystify the ultimate puzzle-solving tool, linear equations. If you've ever stared at a bunch of letters mixed up with numbers and wondered how on earth you're supposed to find the hidden value, well, you are definitely in the right place. We're going to decode this mathematical language step by step.
To make sure this all clicks, we're going to follow a pretty straightforward roadmap. We'll start with the building blocks, define what a linear equation actually is, and then master the art of balancing. From there, we'll tackle variables on both sides, figure out how to reduce complex equations, and wrap up with some real-world applications.
So, Section 1, the building blocks.
Let's get our basic vocabulary down first. In algebra, it really all comes down to fixed numbers and mysterious unknowns. A constant? Well, that's a fixed value that never changes. 4 is just always 4. 7 is always 7. But a variable, which is usually a letter like X or Y, stands for an unidentified number. It's basically a placeholder. Its value isn't fixed until we actually solve the puzzle.
Now, this is super important, knowing the difference between an algebraic expression and an algebraic equation. An expression, like 5x plus 3, is really just a phrase. It has variables and constants, sure, but it's just making a statement. An equation, on the other hand, introduces the all-powerful equal sign. It takes that expression and declares that it's exactly the same value as something else, like 5x plus 3 equals 25. That equal sign is literally the magic key that makes this a solvable puzzle.
Moving right along to Section 2, defining linear equations.
So what actually makes an equation linear and in one variable? Well, first off, it can only use one letter, so just x. No sneaking a y in there too. Also, the highest power of that variable has to be exactly 1. This means absolutely no x squared or z cubed allowed. If you see an exponent higher than 1 on your variable, it is no longer linear. And of course, it's got to have that equality sign. 2x plus 1 equals 7? That is a perfect linear equation. But x squared plus 1 equals 0? Definitely not linear.
All right, Section 3, the art of balancing.
Okay, here is the absolute golden rule of algebra. You have to think of every single equation like a physical balance scale. The left-hand side is perfectly, completely balanced with the right-hand side. To keep that balance intact, whatever mathematical operation you do to one side, you absolutely have to do to the other. Add 5 to the left, you gotta add 5 to the right. Divide the right side by 2, you must divide the left side by 2. It's all about fairness.
Let's actually watch this balancing act happen with a real example. 2x minus 3 equals 7. Our one and only goal is to get x completely by itself. First, we take that minus 3 and transpose it over to the right side, which really just means we add 3 to both sides. That gives us 2x equals 10. To isolate x completely, we just divide both sides by 2. And boom, x equals 5. Perfect balance maintained, puzzle solved.
Now for Section 4, variables on both sides.
I know it might look a little intimidating when x shows up twice, like in 2x minus 3 equals x plus 2. But honestly, we use the exact same logic. We just want to group our variables on the left and our constants on the right. So we bring that positive x over to the left, making it a minus x. Then we shift the minus 3 over to the right, where it becomes a positive 3. So now we're looking at 2x minus x on the left and 2 plus 3 on the right. Simplify that down, and once again, we get x equals 5. Easy, right?
Section 5, reducing complex equations. Get ready because it's time for a bit of a boss battle.
When you're staring down a massive fractional equation like this one, guessing the answer is pretty much impossible. I mean, it looks like pure chaos. The variables are completely trapped inside these fractions with totally different denominators, so how on earth do we break them out?
Well, our secret weapon here is finding the least common multiple, or LCM. Take a look at our denominators, 3 and 6. The lowest number they both cleanly multiply into is 6. So the trick is to multiply the entire left side and the entire right side by 6. This is a brilliant move because it completely vaporizes the fractions. The left side simplifies down to 2 times the quantity 6x plus 1 plus 6. And on the right, the denominator just cancels out entirely, leaving plain old x minus 3. Suddenly, we're back in familiar territory. From there, we just expand the brackets and group our variables.
Following those logical steps just cuts right through the chaos. We get 12x plus 8 equals x minus 3. We bring the x to the left, which gives us 11x. We bring the 8 to the right, turning it into a minus 11. So 11x equals minus 11. Divide both sides by 11, and our exact solution beautifully reveals itself. X equals -1. We went from a totally messy fraction to a super clean -1, just by trusting the balance scale.
And finally, Section 6, Real-World Applications. Let's look at a real-world mystery. Imagine you're told that the sum of two numbers is 74, and you also know that one of those numbers is exactly 10 more than the other. What are they? This isn't just random abstract math anymore. It's a real-world puzzle just begging to be translated. We solve this by acting as a translator between English and math. Let's call our first unknown number x. Since the second number is 10 more than that, we can naturally call it x plus 10. The problem tells us they add up to 74, so let's stick them together. X plus the quantity x plus 10 equals 74. Combine those x's and we get 2x plus 10 equals 74. Kick that 10 over to the other side and we're looking at 2x equals 64. Divide by 2.
And just like that, the equation hands us the answer on a silver platter. If x is 32, our first number is 32. Our second number is x plus 10, which makes it 42. Do 32 and 42 add up to 74? They absolutely do. We literally just translated a real-life scenario into a linear equation to uncover the hidden truth.
Let's try one more real-world scenario, this time dealing with calculating ages over time. So Arun's present age is exactly twice Arav's. But here's the twist. 5 years ago, Arun's age was 3 times Arav's age. Kind of sounds like a riddle, right? How do we find their present ages?
By translating their past and present into variables, we can build an equation that totally balances out their timeline. Let's let Arav's present age be x, which means Arun's present age has to be 2x. Now, let's time travel back 5 years. Back then, Arav was x minus 5, and Arun was 2x minus 5. The riddle tells us that at that specific time, Arun was 3 times Arav's age, so we write it out. 2x minus 5 equals 3 times the quantity x minus 5. We expand the right side and we are locked and loaded to solve. Solving that beautifully balanced equation proves exactly why algebra is so incredibly powerful. We find out that x is 10. Since Arav is x, he is 10 years old today. Arun is 2x, making him 20 years old. Let's double check that just to be sure. 5 years ago, Arav would have been 5 and Arun would have been 15. Is 15 3 times 5? Absolutely. See? The math literally never lies. Ultimately, whether you're figuring out mystery ages, splitting a massive bill, or calculating a perimeter, algebra is way more than just a bunch of random letters thrown onto a page. It is a highly logical language, and it's just waiting to be translated so you can solve the unknown puzzles in your own life. Once you master that balance scale of left and right, you unlock a tool of immense analytical power. So I'm going to leave you with this to chew on. What real-world unknown can you translate into a simple linear equation today? Keep balancing, keep solving, and I'll catch you on the next explainer.